going to be talking about the Hunter experiment, which is the ideas leading up to it are discussed in this archive preprint. We're preparing another preprint that gives more detailed information about the current implementation of the experiment, but that's not up yet. This is a collaboration between Temple University, UCLA, University of Houston, Princeton, and Grand Valley State University with funding from the W.M. Keck Foundation and the Gordon and Betty Moore Foundation. So we're looking for sterile neutrinos. I guess in this group, I really don't have to give a introduction or motivation for sterile neutrinos, but I'll do it anyway. The patterns of multiplets in the standard model leptons are similar to those of the multiplets of the standard model quarks. And in particular, the fact that has been revealed by neutrino oscillation experiments that the one member of these multiplets, the neutrinos, the flavor eigenstates are not the same as the mass eigenstates. And in the neutrino case, as we know, the oscillation patterns imply that the mixing is quite extreme, that these eigenstates are very different from one another. You could contrast that with the strong interaction case where the Cabibbo mixing is rather small. And in particular, in the quark case, we have both left-handed and right-handed members of each flavor generation, whereas in the lepton case, the right-handed neutrinos are missing in the standard model. Now, it turns out that in order, according to the particle data book and people that know, in order to introduce a neutrino mass into the standard model, one must either extend the particle content of the model or else depart from deeply held principles of theoretical physics. And it's this extension of the particle content of the standard model which brings in sterile neutrinos. And there are, of course, thousands of papers in which sterile neutrinos of various kinds, couplings, and masses are introduced, which assist in introducing the small masses of the small masses of the active neutrinos that are implied by the oscillation experiments, and also do other good things for the standard model. So these are analogous to the right-handed singlets of the quark model, and it makes these two resemble each other more. Now, you could also ask how many neutrino flavors are there? This turns out to be quite well constrained by the decay width of the neutral vector boson, which can decay into neutrino pairs. And the measured width implies that the number of neutrino flavors is strictly limited to basically 3. So if you want to add to the particle content of the standard model with light neutrinos, they cannot couple to the neutral vector boson, so they must be essentially sterile. That's basically what's meant by a sterile neutrino, is one that doesn't couple to the vector bosons. So, and as I mentioned before, sterile neutrinos are introduced into the standard model in various ways, and they can help the standard model in various ways, as in the generating masses by the seesaw mechanism, acting as a warm dark matter candidate, and so forth. So sterile neutrinos are a plausible extension of the standard model, and we're going to look for them. So there are various ways to look for sterile neutrinos. They all basically come down to the fact that most sterile neutrinos mix in the neutrino mass mixing matrix with the active neutrino flavors. Since these guys don't do any weak interactions per se, either charged or neutral current, they would be basically invisible except for the fact that they mix with active flavors or through some other interaction that was introduced. So you can do a direct experimental search through flavor oscillations, and there are, of course, what some people regard as tantalizing hints and what other people regard as embarrassing errors in a number of oscillation experiments that look for evidence of an oscillation length which is incompatible with the ones that have already been measured reactor and solar neutrino experiments. Or you can do it another way and try to get a kinematic determination of a neutrino mass, which is larger than the electron volt scale. And that beta decay experiments would fall in this second category, and Hunter would also fall in this second category. So Hunter is a kinematic search for sterile neutrinos that is sensitive in the range between about 20 and 300 keV over c squared of mass. So as I mentioned before, these sterile neutrinos mix with the active neutrino flavors. Great interest has attached to sterile neutrinos as a dark matter candidate, since there are indications, at least according to some people, that the WIMP miracle may not be actually panning out. Negative results for looking for WIMPs are extending down into the region of supersymmetry now, and there are indications from structure formation that the very heavy WIMPs may not be compatible with some structure formation calculations. So people have started to look at light particles and sterile neutrinos in particular as dark matter candidates. Now, the problem with that interpretation is that if some of the dark matter in galaxies is still sterile neutrinos, or at least generic sterile neutrinos, can decay precisely because they mix with ordinary neutrinos. So if you have a sterile neutrino here and it mixes, it has a component of it, which is one of the active neutrinos, active neutrino flavors. That thing is off the mass shell, and it can undergo one of these, a loop decay involving charged leptons to produce a photon and an active neutrino. So this decay would give, it would be neutrino to gamma plus neutrino, would give a monoenergetic X-ray line at an energy equal to half the sterile neutrino mass. And the rate calculated in augmented standard model theory is proportional to the sterile neutrino mass to the 5th power times the square of the mixing angle of that sterile neutrino with the active neutrino. So you could look for these, you could look at local dark matter dominated objects and ask, do we see any monochromatic X-ray line that we can't explain as some other plasma physics or other phenomenon? And if you believe the people that say that they don't see any X-rays, this places very strict bounds on the very strict upper limits on the mixing angle as a function of neutrino mass, sterile neutrino mass. Now, of course, theorists are endlessly creative, so there are articles in the literature where people manage to evade this, but they're not considered mainstream as far as I know. However, in order to be the dark matter, you still have to be around in the present day universe. So the dominant decay mode of a heavy sterile neutrino is also mediated by the mixing, and it also has a rate that has the same dependency on parameters, but it's an invisible decay into 3 neutrinos. So that means that if the mixing angle versus mass line is above this purple line, these things would have decayed by the time the present epoch rolls around, and therefore they could still exist in this range. There are some limits, proposed limits from various observations, but this decay is pretty much invisible, so it's a good bet that if the mixing angle lies above the purple line, the sterile neutrinos can't be the dark matter, but they can still be in existence. Okay, so this brings us to the Hunter experiment. What we're doing is a classic missing mass reconstruction using a particular carefully chosen radioactive isotope, cesium-131, that has a 14-day half-life, decays 100% by electron capture with a Q value of 355 keV. So in the undergraduate version of this decay, it's a cesium-131 captures an electron, turns into a neutral xenon-131 plus a neutrino, and you have a monoenergetic xenon recoil for each neutrino mass. So if you could measure those recoils, you'd have a neutrino mass experiment. Unfortunately, things are a little more complicated, as I'll describe on following slides. But anyway, this is a kinematic reconstruction. It's not an oscillation experiment. We measure the mass by measuring the kinematics of the xenon ion and xenon recoil and the other particles produced. And this has the effect of collapsing the neutrino wave function in the mass basis long after the neutrino has departed the apparatus. Importantly, for this type of a reconstruction, the decaying particles must be rigorously at rest. And accomplishing that, plus other requirements of the experiment, lead to holding these cesium-131 radioactive atoms in a magneto-optical trap in ultra-high vacuum and cooling them to the neighborhood of tens of microkelvin by laser cooling. So in summary, the Hunter experiment is agnostic about whether or not neutrinos, sterile neutrinos are dark matter, and it's agnostic about any particular theory. So here again is the electron capture decay basic kinematics, introducing some of the complications that occur. So in the undergraduate version, all you get is a recoil nucleus and a neutrino, but in the real world, the electron capture leaves behind an inner shell electronic vacancy in that xenon recoil nucleus. And that vacancy relaxes in a complicated way that bedevils the completion of the experiment. Specifically, it emits typically emits an X-ray. This should be a gamma for X-ray, and a one or more electrons are kicked out in the Auger process of relaxation of higher vacancies. So the momentum, because the momenta of the X-ray and the electron are relatively small, the momenta of the recoil nucleus and the neutrino are close to the Q value of the decay. It's the Q value minus the energy associated with that K vacancy. The momentum of the Auger electrons is typically 10 keV over C or thereabouts, and the momentum of the X-rays emitted is typically of the order of 30 keV over C or thereabouts. So the for momentum adding up to 0 can be turned around into this equation, which shows that if you want to know the neutrino mass, all you have to do is measure everything on the right-hand side. The vector momentum of the X-ray, the vector momentum of the Auger electron or Auger electrons, the vector momentum of the recoil nucleus, and the respective energies. So if you just estimate, leaving aside for the moment the difficulty of measuring these other additional particles, if you just imagine it as a two-body decay and estimate the effect of a non-zero neutrino mass on the recoil nucleus momentum, you find that there's an accurate lowest order solution that looks like this. And sadly, it has the neutrino mass squared over the Q value squared in it. So if you're looking for a 10 keV sterile neutrino mass, the effect is something like 0.04%, which is comparable to the thermal momentum of the decaying cesium-131 if it were at 150 millikelvin. So this sets the scale of the measurement accuracy that's needed for this. So we have thought long and hard about this, and there are some key technologies that exist that allow you to do a KV or tens of KV mass sterile neutrino search using these low energy decays. The first thing is that I believe the only real way to get a target, a radioactive sample that satisfies the requirements of this experiment, is to use a magneto-optical trap. So for one thing, it's the thinnest possible radioactive source, so it allows the decay products to escape without interacting and without messing up the kinematics. The density corresponds to a few 10 to the 10th per, oh, this was supposed to be, no, a few 10 to the 10th per cubic centimeter, which is equivalent to something like 10 to the 15th bar. Actually, I think that's supposed to be 10 to the, per millimeter cubed. Don't know how that made it up here. The radius of a Mott trap is is 1 to a few millimeters. The number of atoms in there is between 10 to the 8th and 10 to the 11th with current technology. For a 10-day half-life, that means that you have a source that's 100 to 100,000 becquerels. And the trapped atoms are cooled by the trapping process to in the millikelvin to microkelvin temperature range. Then the measurement technology is also interesting. These are electrostatic spectrometers, basically, that use microchannel plates for detection. And they were developed to provide very high accuracy momentum measurements for low energy charged particles by people that study chemical reactions. So they were made to look at energetics on things that have the energies associated with chemical reactions, which means they have to have incredible momentum resolution. And lastly, you need a large area X-ray detector with high spatial and energy resolution, which we're planning to provide using a fine-grained readout of thin YAP scintillators, which is a scintillator that's used for medical imaging and various other purposes. Okay, so the choice of the isotope, we wanted an important criterion in the choice of the isotope was that we wanted a long enough half-life so that we could stock the isotope in our own lab and not have to debug this experiment at an isotope separator, because it turns out to be quite big and complicated, and better off trying to do it in our own lab. The isotope that we select must be an isotope of a chemical element which is trappable in a magneto-optical trap, which eliminates about 2/3 of the periodic table. And of course, we would like an electron capture only decay, no positrons, which would produce 511s that would require expensive shielding. So, and also we wanted this thing to be available, as in cash on the barrel head. So it had to be a medically used isotope. And if you apply these criteria for the initial experiment, you come up with basically one nucleus that's feasible, and that's cesium-131. So cesium-131 has a 9.7 day half-life, 100% electron capture, no penetrating radiation at all, decays directly to the ground state of xenon-131, which is stable. And it's commercially available for $10,000 an order plus $1,000 a curie. And not only that, but the manufacturer is amenable to working with experimental groups, and they will actually load our atomic beam source so that we don't even have to handle the radioactive material other than to load the source into the atomic beam apparatus. The details of the trigger. We are selecting a single, the capture, okay, we're selecting a particular branch of the electron capture decay. We're selecting a branch where the capture comes out of the K shell, but the refilling of that vacancy comes from the N shell, not the M or the L. Now, why is that? We take a significant hit in rate to do that. The N refilling is only 2.5% of the decays, but the higher energy X-ray, the N is, since it's coming from a higher shell, it emits a higher energy X-ray, will give us better timing resolution, which is critical for the experiment on the X-ray timing resolution. It also results in a lower multiplicity of Auger electrons being kicked out to refill that vacancy that's left after the K vacancy is filled. And also, not only are there fewer Auger electrons, but they have lower energy, which makes them easier to measure. So now I mentioned the particle detection technology. These reaction ion microscopes have been made before. There are several groups in Germany that are specialists in them. There's also a group in Missouri. So this is not new technology. These pictures are from a 2013 dissertation of a 30-centimeter device, or 45 if you include the extraction region, somewhat similar to ours. And the resolution of these things is just phenomenal. This is the transverse momentum distribution of lithium-7 ions. And if you wonder why it's peaked over here to the left and the right, it's because these lithium-7 ions were produced by ionizing lithium-7 neutrals using linearly polarized 266 nanometer photons. So this is showing that the electric field of a transversely polarized photon actually tends to kick the ions out side in the direction of the electric field, and similarly for the electrons. So, and another astonishing fact about these things is that because they're electrostatic, they can have 4 pi acceptance for the ions, because the electric fields are strong enough to turn the ions that are going the wrong way initially completely around. So the MOT is something that is another piece of laser magic that basically acts as a skyhook to confine a sample of usually neutral atoms in ultra high vacuum with no material at all touching them. You can see that if you have 3 pairs of lasers coming in from opposite directions like this, it is not too surprising that you would get, well, you can get, this produces a force that tends to confine the atoms in the center here, and also cools them. I could go through this, but it would take the entire talk. The restoring force in particular depends critically on the presence of these coils here to provide an anti-Helmholtz magnetic field that, combined with polarization tricks, selecting the polarization of these lasers gives you the restoring force that actually holds these guys in the center and damps their motion and cools them, okay? And this is a CCD image of our UCLA collaborators with a 10 to the 9th stable cesium atoms at 20 microkelvin in one of these laser traps. So the overview of the apparatus is shown here. It turns out that in order to get the resolution and the satisfy various other requirements, this thing turned out to have to be pretty large. So it's a tabletop experiment, but as Peter Myers likes to say, you got to have a big table. These are the spectrometers. The ion over here, it has a back-to-back ion and electron spectrometers. Let's see, something similar was done by an experiment by Hindi et al. At Triumph in 1998. This was the group of John Baer. They used a different decay, they used a different radioactive source. They were using the Triumph isotope separator, and we have more ambitious accuracy goals than they do. Now, in order to actually make this work, you've got to master a lot of details, and I'm going to go through these details. I've got 15 minutes left. I'm going to go through these details in a bit of a hurry. So this is not exactly standard reaction ion microscope land. The first problem is that the MOT lasers require a 62 millimeter gap between the innermost electrodes of this electrostatic device. We've got an axial electric field that's provided by these stacks of electrodes that are at graded potentials. That is obviously bad for getting a very uniform electric field at your MOT, but the momentum resolution that you can achieve for the ions depends on making that extraction field very uniform. The use of the lasers also precludes using any grids to separate regions of different electric field in this thing, which is a trick that's used in standard RIM, and I'll talk about in a subsequent slide. Then you have to have one laser nearly collinear with the spectrometer axis in order to provide the 3D confinement of the MOT. And that requires a large inside diameter or some other nightmare configuration for the spectrometer electrodes. And that, of course, affects the field, and it also requires a larger OD, so that makes the vacuum chamber larger and more expensive. Also, the ion resolution, it turns out there's a 1-to-1 correspondence with the best attainable momentum resolution on the ions and how weak the extraction field in the MOT region is. And that, unfortunately, is incompatible with 4 pi electron acceptance. You can still get the 4 pi acceptance on the ions, but at least at the present time, we're only getting something less than 2 pi acceptance for the electrons in our simulations. The electrostatics of this thing was designed using automated sim-ion optimization, which is described in a paper. And that took quite a while. It was my student Shunjian Yu and Francisco Granado who managed to do that. So just some of the tricks of the trade in the reaction ion microscope game. So this is basically a time of flight spectrometer. You're measuring the momentum of the recoil ions and the electrons by time of flight. So for the ions or for the electrons, obviously if you have a source that has a size of say 1 millimeter and you have a time of flight path of the order of 1,000 millimeters, then in this, a simple-minded estimate, you'd say, well, the time of flight accuracy can't be better than the time of flight path uncertainty, which is about a part per thousand. It turns out that there's a standard Mott trick that allows you to beat that, beat it by a very considerable margin. So this trick is called time focusing, and it turns out that if you have a region of electric field with a length L, followed by a field-free drift region of a length 2L, and of course you can only have this if you have a grid in between here. Got to have some place for these field lines to end. You can force the time of flight to be independent of the axial origin of this track. Hard to believe, but basically the guy who's coming from farther away spends more time in the field, so he gets accelerated by a larger amount than the guy who starts from this end. So he comes out of the field going faster, and he catches up. A similar problem exists with the transverse size of the source. The transverse momentum of the ions is measured by the transverse point of impact on the microchannel plate. But if the source was a millimeter across, because that's how big the Mott is, and the MCP is 60 millimeters in radius, 120 millimeter diameter, then you'd think that you have transverse momentum resolution that's limited to about 1%, which would be completely unacceptable. 2% if you take the full width. So another standard rim trick saves the day on this. If your electrodes in here have a big potential step, it makes an electrostatic lens, and that can have the effect of focusing particles that have identical trajectories except for their initial transverse point of origin. Now, this requires a departure from the L2L configuration, but it is possible to make this astigmatic in the sense that both the transverse and the longitudinal or time focusing can be tuned to a single image plane on the microchannel plate. And just to give some examples of this, this is a little hard, this plot is a little hard to understand. Each one of these curves corresponds to a group of ions simulated leaving the Mott at a different elevation angle, a different angle with respect to the line of sight from the Mott to the MCP. So the black ones are directly toward or away from the MCP, and the others are coming off at various angles. And the curves are showing the standard deviation of the time of flight for 10,000 tracks originating at random points within a 1 millimeter radius Mott. So basically, in the first place, you can see that the minimum of the standard deviations is all occurring basically at one position, which is where you put the MCP. And the width is down to it's down to considerably less than a nanosecond for the 0 degree and 180 degree guys. And even for the guys at 90 degrees, the width of this thing is below a nanosecond, which matches the 1 nanosecond time resolution expected from the X-ray detectors, which are what's providing you the start signal. This is a simulation of the transverse focusing, which in the trade is called spatial focusing. So here you have two groups of ions starting from different transverse positions. This is very exaggerated. It's 10 millimeters. It's 10 times as big as the Mott. And the different colors correspond to different angles. So different transverse momenta. And you see that the different transverse momenta all hit the MCP at exactly the same place, despite the fact that they started out 10 millimeters apart. So this is a result of over a year of work by these two students, they basically developed the method of optimizing these things, automated optimization using SimIon. I mean, SimIon is set up to do that, but they developed the method for doing it for this experiment. And we've done quite a lot of simulations at a pretty high level. So we now have a simulation stack going on where we produce the three-dimensional electric field maps from SimIon. You need a magnetic field in this thing to confine the electron tracks to keep them from spewing out the sides. And SimIon has a lot of, well, we produce the 3D magnetic field maps from using COMSOL, and we've now gotten rid of SimIon for particle tracking, and we're using the particle tracker in Geont 4 and importing these 3D field maps. And then, as you can see over here, the analysis is being done with Root. So these are curves that correspond to detecting electrons, and you have the time of flight for the electrons on one axis and the so-called splat radius, that is the radius at which the electrons strike the microchannel plate. And all these different families of curves, the different colors correspond to the initial energy of the electrons. And along here is the, well, what's producing different times of flight for the same energy is the initial angle. So this becomes quite complicated. Using Root, we can impose cuts that eliminate these confused cases over here that are happening because of the constraint to a relatively weak extraction field for the ion resolution. Now, another thing that has to be taken care of is magnetic shielding. So this is the magnetic field in the lab at UCLA where this thing is going to be located as a function of time for 24 hours. And there are magnetic fields in the neighborhood of hundreds of milligauss, and they vary with time. So we need a magnetic shield, and we need a solenoid, as I mentioned earlier, to confine the electrons. So again, there's literature on this, but it's not easy to do, especially because if you recall, this vacuum vessel has a lot of large penetrations right in the middle where the electrons have the lowest energy and where they're most sensitive to stray magnetic fields. So we had to figure out how to make a magnetic shield that would not only carry the return flux of the 6 Gauss solenoid, but also shield out these ambient fields. And that was admirably accomplished by Shunjen. These are the residual fields inside the spectrometer, which are in the neighborhood of a fraction of a milligauss, depending on whether you impose an external field, which is, let's see, transverse or longitudinal on this thing. So there's a lot of design work has gone into this. And we've simulated the neutrino mass reconstruction for this, the high acceptance tune that we're using, which has a 4 pi acceptance for the ions onto a 120 millimeter microchannel plate. You get a, of course, the Gaussian doesn't fit this very well, but never mind, doesn't have to be Gaussian. Anyway, the sigma is around 300, this is mass squared, 300 keV squared. We have also devised a high resolution tune. So what's the limit on this resolution? It's essentially the number of transverse resolution bins you have on the microchannel plate. If the microchannel plate is only 60 millimeters in radius and it has a resolution of about 1/10 of a millimeter, you're limited to a part in 600 resolution on the transverse momentum. And if you want 4 pi resolution, 4 pi acceptance, that means a part in 600 resolution on the overall momentum. If you give up the 4 pi acceptance and you just try to see how good of a resolution can Shunjen get, the answer is more like a sigma of 100 keV over c squared, but you only have 1/8 of the acceptance unless you get a much bigger MCP or an array of MCPs, which are becoming available now. Physics backgrounds, we've analyzed and simulated many physics backgrounds. The most important one turns out to be a nasty. It's, sorry, that's not electron ion, that's supposed to be atom ion scattering. the xenon ions, they're ionized because they emit Auger electrons, actually have a nasty scattering process with the neutral atoms. This is supposed to be atoms in the MOT. And they induce a dipole moment on those atoms, and then they scatter by Langevin scattering. This has the effect of broadening the zero mass peak and contributing a flattish background. This may be controllable in later iterations of the experiment using a lower trap density or a long skinny trap, but for the present, we're gonna live with it. There are also, of course, backgrounds due to the fact that an MOT is actually a rather leaky trap. The typical lifetime of an atom, the length of time that a trapped atom actually stays in the trap before it leaks out is in the neighborhood of hundreds to thousands of seconds. So, which is of course much shorter than the radioactive decay time of the radioactive cesium we're using here. So the radioactive material is constantly escaping from the trap, and it's depositing on surfaces inside the experiment. Now, fortunately, the lines of sight in this thing are very constrained, with the exception of the line of sight from the MOT to the X-ray detectors. So we've simulated and considered this in some detail. The accidental coincidences will grow with time as you get radioactive source material building up on the X-ray panels. After 4 or 5 days, you're going to have to do something to reduce that, because the true to accidental rate will be something like 1. And this can be done by desorbing the radioactive material from the X-ray panels using pulses of UV light. And we've incorporated large viewports into that central region of the vacuum vessel specifically for that purpose. So I don't have time to go through all these calculations, but we believe we understand the rates and the true to chance ratio and so forth in this experiment. So this is a simulated discovery plot where what we have here is what it would look like if you had 40 sterile neutrino events. This gives a 5 sigma peak at neutrino mass equals 60 keV over c squared. And the 40 events in a year of running would correspond to a mixing angle of about 3 times 10 to the minus 4, which is the claimed limit on our the plots that we show around, okay? The components of this are the accidentals is a flattish background somewhere down here in the purple. The ion atom scattering, at this time at least I got it right, ion atom scattering, not ion electron scattering, gives you this, the green curve with the zero mass peak is obviously running off scale up here. And then if you add in all the backgrounds and the finite mass sterile neutrino, you get finally the purple curve here. So we claim to have sensitivity in the range between 20 and 300. You run out of gas around 300 because the Q value of the decay is only about 320 of the underlying primary decay. All right. So these are what the anticipated results look like on a plot of existing limits, mainly from the 17 keV neutrino era using beta decay. And Ice Cube is over here. Of course, that's measuring a different mixing angle. That's measuring the mixing with a muon neutrino. And I believe these incorporate the present Catron and related experiments, which are down in the lower mass range, lower than where Hunter is sensitive. Now, there's actually hardware on the floor here. The Keck Foundation gives you a check for the full amount on day 1, so you can buy things at your own pace. And this is what's going on here. So the UCLA people have done a tremendous amount of hardware work. I don't have time to really explain this orthotropic atomic beam apparatus that they've built, but it produces an atomic beam a collimated, almost a focused atomic beam without using any actual focusing elements, and therefore without wasting all of your radioactive material on the inside of your atomic beam apparatus. The way this works briefly is that the inside of the oven is coated with a material that has a work function such that if an atom hits it, it spits it right back out. And the only atoms that these things that can actually get out of this box are ones that are going in this particular direction. This is the vacuum vessel. We spent over a year and a half designing and getting the, working with the manufacturer to actually get this vacuum vessel built. It's built, it's on the floor at UCLA. It seems to have alignment and properties that will satisfy our requirements. There are several parts that are not yet finalized. We need some re-entrant ports for vacuum isolation of the X-ray panels. That's a little technical. I'll explain it if you want later. Also, the solenoid system and the magnetic shield, the conceptual designs are done, but the mechanical design, where do you actually hang these pieces of metal from, given the existence of the stand and so forth, has not been completed. And the trigger, the conceptual trigger scheme, we know we're triggering on an X-ray and a coincidence of one or more Auger electrons within 100 nanoseconds, and then looking for a decay ion that arrives several hundred microseconds later. But the actual hardware for this has not been finalized. Now, the limit plot here showed, where is it? Showed several phases of Hunter. So how do we plan to reach these increased levels of sensitivity? In order to do that, we have to have a stronger radioactive source, so more atoms in the trap. We have to have more X-ray detector coverage. This is this combined with the L refilling X-ray, the N shell refilling is another. These two are our big hits in efficiency of data collection rate for this experiment. So we'd have to go from 8 or 9% X-ray coverage to as high as we could possibly figure out a way to do. We'd have to accept more X-ray transitions, which imposes significantly difficult requirements on the X-ray detector. And we would have to use a different isotope with a shorter half-life so that we get more decays in the trap. And that will require in the future iterations of the experiment to operate at an online isotope separator. But by then we should have the thing debugged, so it won't be as painful. Just to give you an idea, these are the elements of the periodic table which have been magneto-optically trapped. So the requirement that you can trap these things rules out a good part of the periodic table. We actually did a search with Alexandro Sonzogni, I hope I pronounce his name remotely correctly, from the NNDC. These guys will help you do searches of the rather recondite database of nuclear decays. And we found that there were a number of candidates for a second or third generation Hunter, which had short half-lives and less than a 25% branching ratio to nuclear gamma rays, and less than a 25% positron decay branching ratio. So these could be manageable candidates for a next generation Hunter. So the current plan is we've started the hardware in 2020. We're making final parts orders now. We hope in the next calendar year, God and COVID willing, to complete the assembly of the thing and commission the vacuum system. Once that's done, we can go ahead to commission the MOT systems using stable cesium-133, add the magnetic shields, and then commission the full system using photoionized stable cesium, and then finally work toward a radioactive cesium fill. And I believe that is the last slide.
Great. Thank you, Jeff. That was a great talk. Right. So let's see.
Should I stop the share or keep it on?
It would be helpful to keep it on if it's the question is relevant to
Okay.
what you want to show. There is a question from Andrew. Andrew, would you like to read the question?
Sure. Hi, Jeff. It's Andy Shimkowiak. What's the magnitude of the field from the optical trap Helmholtz coils? And will that field affect the electron trajectories any?
It has to be operated as an AC mod, so we have to turn the field on and off. And we've done a lot of work simulating the eddy currents and the effects of doing that, but that is an established operating mode for an MOT.
Okay, thanks.
Otherwise, you're right, it acts as a fine magnetic mirror, killing off completely the electrons.
Okay, looks like I don't see any other questions. If someone has a question, please feel free to ask right now or raise your hand or type it in the chat box.
Can you go back to the schedule, Jeff?
Is that me or you? That hissing.
So when do you plan to have your first data?
It's somewhat up in the air now because we're being heavily constrained in the working by the COVID situation, especially in Los Angeles and the air travel and so forth. I would hope that by the end of next year, we'll have radioactive cesium in the thing.